Hello everyone, I'm Olga Moskvyak from Queensland University of Technology, and I'm presenting a paper Keypoint-Aligned embedding for image retrieval and re-identification. Learning pose-invariant image embeddings is crucial for visual search tasks such as image retrieval, person or vehicle identification. The existing approaches for these tasks suffer from high interclass variance due to deformable shapes and different camera viewpoints. For example, the same car looks differently from the front and the rear, and the appearance of a bird changes dramatically with its activities, like flying and sitting. To overcome this limitation, we propose to align the image embedding with a predefined order of key points. More specifically, we learn a keypoint-aligned embedding that consists of subvectors where each subvector encodes a specific key point. Example of the bird, the embedding has subvectors for tail, the subvector which encodes belly, eye, and a beak. Our keypoint-aligned embeddings model, KNet, explicitly learns subvectors representing each key point in a multitask fashion, guided by the auxiliary task of key point reconstruction. Multitask learning allows us to jointly optimize both localization of key points and learning discriminative image embeddings. The backbone of KNet is a convolutional neural network that outputs a feature map. This one. We use ResNet50 in our experiments. The motivation of our work is the observation that different channels in the feature map extract various meaningful parts of the images. Building on the idea that only a subset of the channels in the feature map is activated for each key point, we propose a chi block to select these channels. The model assigns one chi block to each key point. During training, the model outputs a keypoint-aligned embedding, class scores, and key point heat maps for each input image. During inference, only the image embedding is computed. A chi block is shown here on the right. It accepts a feature map with number of channels is represented by capital C, and in case of ResNet50, the number of channels is 2048. Channel scaling and channel selection parts reduce the number of channels to a much smaller number, which is 64 in our experiment. Ultimately, the key point embedding produced by each chi block is concatenated into a key point aligned embeddings. The KNet is trained with a combination of losses which jointly optimize the main and auxiliary tasks. We analyze our method by visualizing class activation maps. We observe that class activation maps for the baseline model in the first column are activated mainly around the head, while chi blocks focus on different parts of the bird. We compare our KNet against the state-of-the-art for image retrieval on various datasets. For retrieval, the dataset is split into training and testing subsets with disjoint classes. The retrieval metric, recall at R, is a percentage of the testing examples whose set of R nearest neighbors includes at least one example of the same class. Most previous works in image retrieval are metric learning methods. Our method adds pose information to the embedding learning and outperforms the previous works by a large margin, achieving recall at 74.2% on birds and 91.1% on cars. Finally, let's look at some examples of matches using our method on a dataset of fine-grained bird species. The first column is a query image, and then in each row, the 5 images are the matches returned from a database. We can see that our model found the matching bird classes with a percentage of large pose with the presence of large pose variations, including flying and sitting poses. Thank you.